This instructional video is about the free particle. Free particle is unique in all of the model systems in that it has the simplest explanation, but requires us to draw on a number of different influences from what you would have learned earlier in a full course in quantum mechanics to get a full and proper explanation. So the free particle is simply a particle that is existing in space, free from the influence of any potential or energy fields. This means then that the Hamiltonian for the free particle looks a lot like what we would normally have, except that with the minus h bar squared over 2 times the mass term, all we have is the second derivative in all of three-dimensional space. Now, from a philosophical perspective and an instructional perspective, if you're not getting into the hardcore quantum mechanics and very highly detailed, then it can be convenient to think, at least starting out, in just one dimension. So we'll pick the x direction. And in this case, because we don't have any boundary conditions, we don't have any potential, all we have to do is find something that would be an eigenfunction of this second derivative. And that's sines, cosines, and exponentials. Well, it turns out that we have an exponential that would combine everything by using Euler's formula. So if we recall, we can use e to the plus or minus ikx, and that gives us cosine kx plus or minus I sine kx. And so this incorporates sines, cosines, and exponentials perfectly, and we've got something that's going to work when we take the second derivative to give us the function back. So once we have a candidate for the wave function, well, we'd want to try to normalize it. So if we let this be our wave function, then we need to normalize it, at which point we set up our typical integral to do so. So integral over all space, in this case that's literally from minus infinity to plus infinity. And we want the conjugate, so I'm changing the sign on the imaginary part, times the regular wave function. And that entire thing has to be equal to 1. Now at this point we recognize that we would pull the normalization factor out completely, leaving us with e to the minus ikx times e to the ikx. Combining those powers in our exponentials leaves us with the e to the 0, which is just 1. And so now what we're faced with is a squared integral dx equals 1. It should be pretty readily obvious that, well, once we integrate this dx, we get x plus infinity minus a negative infinity. That's infinity, and now we're stuck with something that's going to be kind of terrible because, well, if we do 1 over infinity, that looks a lot like something that should be 0, and your calculus and all of your limits and everything can't save you from the fact that that doesn't make much sense. So what we have to do then is move away from this idea. This is fine if all we're going to do is talk about it in a very general sort of way, but the instant we want to use all the nice things that we get from having things like orthogonality and normalization, this becomes impossible because, well, you just can't normalize it. However, we can take an influence from an older idea. So rather than take this route, we can recall something else, which is that the first postulate tells us that we can build a wave function. So we're going to recall the first postulate, that the wave function of the entire system can be built up as a linear combination of smaller functions. And so this approach leads us to the big idea behind talking about a free particle. And that is that we can take a bunch of what we call plane waves and combine them into a wave packet. And so the idea is that we could take a bunch of individual things that we couldn't normalize separately, which is what we have here, and by combining them, writing those out as plane waves, we get a wave packet. And so we bundle all of them together effectively to create a representation of that free particle. And so what that looks like is the following. So we can have a wave function, and in this case we can incorporate time, since that's also an exponential solution. So we have some normalization out front, and we have to introduce some new ideas. This effectively is an integration in three-dimensional space over the vectors that are going to direct our wave packets and give that combined set of plane waves an energetic identity. So this is E, I, K, X, A, R, minus omega T. And so while this representation looks really complicated and possibly a little bit crazy in comparison to what we might normally think of in a single dimensional case, or lest you forget, unnormalized, this can be. And so the idea that we have in place is that because we have this different representation of things, this allows us to actually take advantage of some of the other ideas that pop up in a study of quantum mechanics. Most prominently, the wave-particle duality of light. So when we think about something that has wave-particle duality, it can behave as a particle, which is the whole idea that prompted all of this work behind the free particle. But it also can be represented as a wave, which using plane waves combining into a wave packet allows us to do. And as a result, we can then talk more effectively about the ideas of quantum mechanical tunneling and scattering that apply to the quantum mechanical free particle. And it all has to do with the fact that we are combining a bunch of individual vectors together to give us something that we treat as one. And we can then talk about the fate of the individual parts of that combination when it comes into contact with something else. And we use this sort of thinking of an unnormalized single wave to talk about those individual parts. So when you're thinking about free particles, it's important to pay attention to the context. If we are just trying to be conceptual, it can be useful thinking in these terms. But if we're trying to be practical and actually use this and do the math, or more accurately, have something do the math for us, then we want to start thinking about these things in terms of plane waves combining to give us a wave packet.